Okay, let us continue. So last time we started to discuss the notion, right, of a random variable. And so basically, a random variable, right, is a random number generator, right, in some way, or is something that takes on numerical values randomly. Okay, and so the sort of things we're interested in is to calculate this kind of probabilities, or kind of more precisely, right, given a description of a random variable, how do we work with it, and how to work with it, at least at the beginning, involves calculating, right, probability of events connected with X like this. Okay, and a random variable basically can be viewed, right, as a implicit sample space, meaning that it's definitely connected with probability and events and outcomes, as we discussed it, right, in the previous 5 lectures or so, 4 lectures or so, right? It's just that now the sample space where it comes from is not explicitly displayed, but the values you take, right, will kind of serve as the sample space itself. But that's all there is, right? So basically, sample space that somehow is associated with numerical values. And so to work with a random variable, okay, the first thing that you should always get into a habit of is to question what values the random variable in question can take. This helps you get oriented, right? It's just exactly like you should ask what sample space you're considering. It helps you oriented to possible outcomes, or here, right, possible values the random variable can take, from which, right, you can work with the random variable with the correct picture, namely with the correct possibilities, right? And then, right, we move on to kind of mention the distinction between discrete and continuous random variables, or these are the two main classes of random variables we'll be considering in this course. Or, in many other courses, you mostly see random variables divided into these two camps. Okay. The number one distinction, or the easiest way to distinguish them, is that discrete random variable can take on a particular value, right, with a, sorry, this is continuous, take on a particular, right, value with positive probability, right, actually those are called point masses, right? It takes on point masses, while a continuous random variable does not take on any point mass, meaning, right, that the probability it takes on any particular value is 0. Okay, but just because it does not take on point mass, meaning it doesn't have mass at a single point, right, doesn't mean that it does not have mass over an interval. Okay, so in that sense, these, right, the probability less than or equal to A, between A and B, bigger than B, are meaningful for a continuous random variable. Not that it's not meaningful for discrete random variable, but for discrete random variable, because we see discretely what values it can take, a lot of times we are not exactly interested in probabilities fall into some intervals. I mean, like we can pose those questions, but from like the characterization point of view, it's not essential, right? We can zoom into one point. But for a continuous random variable, by necessity, we have to consider its behavior on an interval, okay? And then just to remind you, these are two neat distinction or categorization that would serve us, right, for this course and many other, let's say, beginning courses in probabilities and statistics. But random variables in general don't have to fall into either one of these camps. They can be neither discrete nor continuous. In which case, right, I mean, the tools that we describe, some of the tools may work, but some of the tools may not. For example, right, the notion of density, which is the notion exclusive for continuous random variable, may not apply exclusively to something like this, but it can be applied where appropriate, for example, inside this interval, okay? Things like that. So again, it's a more advanced concept, which well, you will only see it once here in connection with the CDF, with the cumulative distribution function. Exactly, because the CDF, right, is a tool that sort of describe a random variable unifyingly, meaning that, right, doesn't matter which random variable we deal with, we can consider as CDF, okay? But to backtrack a little bit, right? So what we're discussing was how to completely describe a random variable. Or put it another way, right? How do you know that you have enough information to work with a random variable, right? Because sometimes you're given less information than you need. How do you know so, right? And so for the difficulty is that there are multiple ways to describe a random variable, depending on what you have to begin with, right? For example, if you have a discrete random variable, then describing, right, is point masses for every relevant point mass, right? Meaning the ones in the support will be enough, right? For a continuous random variable, then because point mass, right, doesn't mean anything, or not doesn't mean anything, but is equal to 0, right, for continuous random variable, then we have to do something else. And to do something else, well, for now, right, is only to capture it over an interval, for any interval, right? So basically, if you can capture the probability falls into any interval, if you will, then you would know its behavior everywhere, okay? Now, and then, right, there are other ways like the moment-generating function that we'll be discussing at the end of this course, meaning that there's not a single way, right? But there are multiple ways. And the next lecture, next couple lectures or so are exactly about kind of zooming in, right, these classes of random variables specifically, and then go through, right, different, let's say, classical examples of random variables and how to describe them. But one thing, right, that comes out of this is like, you know, seems like different random variables have different ways to be described. And that's not so, or doesn't have to be so, right? There could be a single device or single concept that can be used to capture a random variable, right? And that device is called the CDF, okay? And the CDF is a important conceptual tool to know, not only because, you know, theoretically, right, it serves as the unifying way to categorize a random variable, but also that in a continuous random variable, to basically work with continuous random variable efficiently, if you don't know how to go through the CDF, then basically you cannot work with a continuous random variable. So we'll see that later, right? But a CDF, right, is basically just the probability that the random variable, right, lies to the left of A, right? But including A, right? Including A. This equality is important, right? And that's the definition, right? So if you can know these values for all A's, right? This is the axis of A right here, right? Then you basically, the claim is you know the random variable completely, okay? And the CDF, right, is not arbitrary, like meaning it cannot just be anything you want it to be. It has several characteristics. It must be between 0 and 1 because it's a probability. It must be increasing, or, you know, the word increasing here is more like non-decreasing, but, you know, in some circle, increasing is when we mean strictly increasing, we'll put that word in. Basically, it can be constant, right? It can be constant, but it cannot go down. That's all, right? It cannot go down, right? This is not allowed, but it can be constant, right? It can be constant for a while. So yeah, right, not decreasing. And because, right, as you keep going to the right, you will have more and more, right, chance to be less than equal to that value, Okay, that's why the probability can only gets more, right, or not decrease. Finally, right, if you go all the way to the right, you will reach the upper limit, which is 1. You go all the way to the left, you reach a lower limit, which is 0. Okay. And so all CDF must obey this law. And the relevance of the CDF, right, in terms of how it recovers probabilities are the following, right, including the last one. Meaning that, right, you can recover all sort of probabilities, statements you want to say by using the CDF, okay? So I guess the last one is here, right? Right here. Including, right, the point mass. Right. So, right, you have 1, 2, 3, 4, 5 statements, right? That basically, in some sense, right, could capture all you want to ask. All you want to ask about the probability of a random variable, right, at any point. And the CDF would allow you to compute that, okay? Now, but we need to kind of understand the CDF a little bit more, right? And just kind of like to get into the details here. So if you have a discrete random variable, right, this is where we stopped last time. If you have a discrete random variable, then its CDF, I guess, this is the question, will be a pure jump function, okay? And it will jump where, right, the random variables takes on point mass. For example, right, we give example of the dice, right, toss 1, 2, 3, 4, 5, and 6, right? And so it'll be 0, right? So this is X, this is the CDF, right, of the dice toss, right? At 0, right, it will jump to 1, 6 and stay constant for a while, right? And then jump to 2, 6. Sorry, circle here, dot there, circle, dot, 3, 6, 4, 6, 5, 6, right, and 1. Like that, right? Okay, so this right here is 1. And so, right, it's important for you to kind of understand, right, why a discrete random variable can only have a CDF this way. Or put it another way, right, this is how you would know, or this demonstrates why a CDF allow you to, right, know a random variable. Meaning a graph like this can only be the graph of a discrete random variable, okay? So again, because, you know, it tells you that the only way, right, that it gains probability is through a jump, which is a point mass. So that's a discrete, right, sign. Otherwise, it stays constant, meaning it cannot gain mass in any other way. It cannot gain probability in any other way, right? So therefore, it's a discrete random variable. So intuitively, right, in terms of physics, or what this is saying is, you can think of basically there's 6 masses hanging, right, at these points. Each of them has mass 1, 6. What the CDF does is just sweep it from left to right, okay? And so its CDF is cumulative. So basically, it just count the total masses, okay, it has seen so far, okay, along the way. And if you want, you can say this is the mass of the universe, right, whatever that means. So here, your universe has 6 point masses, right? If you go from the left, right, your universe, right, you have encountered no mass so far, so you stay at 0. You go through a point mass, right? So you have picked up a mass 1, 6. That's your total mass so far right now. But then you stay constant because you have encountered nothing else, right? and so on, until you reach here where you reach all the masses of the universe, meaning you reach value 1, and then you stay like that forever. Okay, so that's the meaning of the CDF. Any question? Now, a continuous random variable, right, on the other hand, would sort of display the opposite behavior. Okay, so the CDF of a continuous random variable should not have any jump. Okay, the CDF of a continuous random variable should not have any jump. In fact, right, it should be even differentiable, and right, the derivative of the mass function, the CDF here, is called the density function. And that will be a very important object that we'll be looking at for continuous random variable. So in fact, right, the PDF right here, which is this one right there, will be the key, right, feature of a continuous random variable. And so basically, right, yeah, this is what I'm saying, right? Basically, this, again, with the mass analogy in physics, and this is exactly what it is, you can think of, right, basically, again, the same picture, but you have a thin wire, right? You go from left to right, but what you have, right, is wire that very thin, right? So at any point, you have no mass, but you have a density of this wire along the way, right? As described right here. So as you go along and you measure how much weight the wires so far have, you might have something that looks like that. Is that okay? So basically, right, as you go along, you pick up more and more mass, but you pick up the mass continuously because, right, the wire has no point mass hanging on along it, but it only has mass density. So a very, very thin wire, right, that's stretched along the real line. Does that make sense? So, right, basically, it must be continuous, has no jump, because a jump, right, would basically be describing a point mass, right, at that. So a discrete value. So no point mass, continuously move increasing. Okay. And so from that point of view, right, a random variable whose CDF has both features will be, right, a mix of discrete and continuous, which is really like, you know, a case that we only introduced you once in this course, but won't go too much into it. All right, any question about this? All right. So let's take a look at this question number 5, right? Okay. So in this question, you're given a CDF, right, which is described as a piecewise function. All right, whatever it is, right? It can be described in any way you want. Now, the question is for you to figure out these probabilities, right, from the CDF. So basically learning how to work with the CDF itself. Okay, so let's give that some time for you to take a look at and try to figure it out on your own. Okay. So it's not asked for here, but for this problem, right, it's instructive to sketch the CDF just to see what's going on, right? So right, B whatever, or right, it starts at 0, right, which is supposed to be for a CDF, right, up to 0, right? And then at 0, it jumps to, or what, hold on, it's B over 4, right, from 0 to 1. So it goes to 1/4, right, like that. And then the value at 1, right, is 1/2. So there's a jump there, right? 1/2. And so like that, right? Notice it's less than here, less than equal there, right? So, and then it still continue with slope 1/4. So parallel to that, right? And then let's see, right? If at 2, then 2 minus 1 is 1, 1/2 was 1/4 was 3/4, right? And then here is 11/12, right? At 2, so yet another jump, right? So because 3/4, right, is 9/12. So, and then it stays there, right? And then at 3, it jumps to 1. And then stay there, right? Okay. So any question about the graph? All right. So even before we answer these questions, right, let's ask, is this a discrete or continuous random variable? From the CDF.
Discrete,
Why?
because there's jumps in.
True. I mean, it has point masses. You're right. It has jump. But let's go back, right? This is why it's subtle. Notice, right? The CF of this grammar will be a pure jump. Do we know what the word pure means? It means, or right, maybe another word for it will be step function. The word pure here means besides a jump, it does not do anything else. All right. Pure jump or step functions are the same thing, meaning that besides a jump, it's flat. Again, right, let's make sure we understand it. Why must it be flat? What happens if it's like, let's say, tilt up like that? If it tilts up like that, that signals that the mass here, right, is not the same as the mass here, right? The cumulative mass, the total mass here is not the same as total mass here. But why would that happen? Because it gains mass from here to here. But there's no jump, right? That means it gains mass continuously. From there to there. Do we understand? So if, right, it goes up continuously, that means it has gained mass during that interval. But if it gains it continuously, then it's a continuous random variable, or it behaves continuously in that part. But if we say it's discrete, that means it cannot do that, right? It can only have point mass. Do you understand? So back to this graph, right? What do we see? Is it a pure jump function? Answer? No, right? These parts right here, yes, right? But it's not a pure jump here and here. So this random variable, as described by this CDF, is neither discrete nor continuous. Do you understand? There are some parts where it take on point mass, and there's some parts where it gains mass continuously. Okay? And let's follow that up with a question, right? Where are the point masses? Where does it take point masses? It will take point masses right where it jumps. So exactly where they ask this question. Right? These are where the point masses are. What about probability x equal to 0? What would that be? What's probability x equal to 0? So remember, right, this statement. So probability x equal to 0 is f of 0 minus f of 0 minus, which is what here? What is the value? if we look at the graph, right? The graph is continuous here. So, right, f of x at 0 actually, well, from here, right, is 0, 4. And the left limit, right, is from here, which is 0. So, right. So 0 is not a point mass. Okay, but 1 and 2 and 3 are. Any question about this? All right. So let's answer part A. What are these? Any suggestions? So, right, the same formula will work for all points. So that will be, well, f at 1 minus f of 1 minus, right? F of 2, f of 2 minus, f of 3, f of 3 minus. Well, f of 1 is here, so 1/2, right? Plus 1 minus 1 over 4 minus 1 minus is here, which is 1/4. F of 2 is here. F of 2 minus is here. So that will be 1/2 plus 2 minus 1 over 4. F of 3 is here. And then f of 3 minus is here. Any question about this? Okay. Well, part B. How do we compute this? Any suggestions?
Is it fx of 3/2 minus fx of 1/2, and then minus the p of p1x at 3/2?
That's excellent, right? So what you said is perfect. So it would be like that. That's perfect. And how so, right? Because what is fx at 3/2? Fx at 3/2, right, is probability x less than or equal to 3/2, right? And fx 1/2 is probability x less than or equal to 1/2, right? So a priori, if we subtract these two, what we'll be getting is probably 1/2 less than x less than or equal to 3/2, which is not this, right, in form. So you have to subtract that one, right, to make sure they're equal. That's perfect. Now, of course, we can plug in 3/2, right, into here, here, right, and 1/2 into here, right? But what about probably x equals to 3/2? How do we find that? What is probably x equals to 3/2?
Wouldn't it be 0 since it's on the continuous line there?
That's correct, right? It's probably x equals to 3/2. If you want, is f of 3/2 minus f of 3/2 minus, but 3/2, right, is here, and right, the value of the function and the left limit would be equal, so that's 0, right? And so if you plug in, you'll get what they are. So, right, alternatively, here, instead of subtracting 3/2 like this, right, subtracting this, you could do f of 3/2 minus, right, which will have the same effect, because you see, right, f of 3/2 minus exactly is probably x less than 3/2, right? So this is perfect. This is fine. But if you combine these two, you'll get that. All right, any question? All right. So basically, right, that would be all there is for a introduction to random variables in terms of, you know, what they are, what we should try to attempt, right, to characterize them. So to recap, right, discrete random variable you need to know is so-called here, this is mass function or PMF, probability mass function. For a continuous random variable, it's down here. You need to know their density function, which, right, is the derivative of the CDF. And finally, right, you should have some idea of what the CDF is and how they behave, right? Because CDF is the tool that is common for all random variables. Okay. Now let us finish up with, I guess, the two remaining questions, right? All right, let's take a look at 3, right? So the point of 3 is nothing fancy. It's just a probability question. But here it kind of casts that, right, in terms of a discrete random variable. Hopefully you see that. And so it asks for the mass function. All right. So to start with, what values can this take? So are we sure it's a discrete random variable? And we know that, right, by looking at the values it can take. What is it? What are they? Okay, so what values can X take? $500, 1,000, 1,500, and 2,000, right? These are the only possibilities, right? That's why it's a discrete random variable. Now, what are these probabilities? What's the probability is 500? Correct? What about 1,000? Right? 1,500? 1,500 actually is the same as 500, I think. What about 2,000? No, 1,500 is what? 1,500 actually, I think, is actually still this, right? What about 2,000? No, 1,000 is wrong. This 1,000 is wrong, right? 2,000 is, so do we see why 1,000 is wrong?
There can be
First of
only
all, right,
one.
what must happen?
Sorry.
Yeah, go ahead.
Oh, there's can be only one person by the 1001.
Correct, right? So first of all, right, the way we know that, or first of all, right, what must all these entries do? All these entries, right, whatever you calculate, they must add to 1, right? So however you do your calculation, they must add up to 1. So if you can't have that, then there's a mistake somewhere, right? That's one way. Why must they add up to 1? Because, right, that's all the possibilities, right? And right, so here with 1,000, so basically, right here, what we have calculated is 500, 500, right? But we have not calculated 1,000, 0, right? Or so that's going to be right twice times 1/2. Well, it's not twice. It's really actually this one, right? Okay. And then this is 1,500, right? Or 500, 1,000, right? So what's missing here? Times 2. This is 1,000, 1,000. This is 0, 500, or 500, 0. All right. Any question? All right. So let's take a look at 4. Okay. So again, right, this is just really a probability calculation question, right? Cast as a discrete random variable. But here, right, you also, another point of random variables, you have to read, right, the description of the random variable. You may have something in mind, but the random variable requested is something else, right? Notice here, X is the number of times player 1 is a winner, okay? And so pay attention to that as we answer the question. So the possible, right, values X can take has been listed out for you, right, as 0 to 4. Again, just try to verify that that's indeed the case, right? That's the support of the random variable. And, right, see if I wrote that there. I guess I should, this is not right? It should probably X equals to rho X. Okay. So, right, so let's see. Right, these are just distinct. So basically, right, each person, right, is equally likely to get a number between 1 to 5, right? But I guess not independently, right? Because you distribute these numbers among these people. So anyway, right? What's the probability that X equals to 0? What does x equal to 0 mean? Means the player 1 compared with player number 2, right? And the number of the player 1 will be less than number of player 2. What's the probability of that? Should be a half, right? We know why. Because by symmetry, right? Player 1 less than player 2 should be same as player 2 less than player 1, right? There's no distinction between these two players. But then, right, you add these two up, it should be 1 because these numbers are distinct. Therefore, each of them is 1/2. Okay. All right. So I guess it's time for your quiz. We'll continue back to this after the break. So for your quiz, let's have you look at let me see here. All right. So let's have you look at the salesman question. Okay. All right. Any question before we take a break? Okay. So let's continue at 7:05.
Professor, I couldn't submit it in time. Is it okay if I email it to you?
Try to, yes, but try to submit on time, okay?
Okay, sorry about that.
All right. Any question before we continue? Right. So right. So here, probably x equal to 0, which is the player 1, right? Not win any game is 1/2. Level 1 was probably x equals to 1. Any suggestion? So how is it that player 1 can only win one game? It must be the case, right? That player 1 wins over player 2, right? But loses over player 3, right? What's the probability that this would happen? So there are 3 factorial ways, right, to arrange distinct numbers between the 3 players, right? And this order, right, can only happen one way. So that would be 1 over 3 factorial, right? Any question about this? What about 2? Any suggestion? How is it possible that player one wins 2 games? Well, it must be the case that he wins over player 2 and 3, right? But lost to player 4, right? And how many ways can, or what's the probability that this will happen? Well, there are 4 factorial ways, right, to arrange numbers, right, between 1 to 4, right? But there are 2 ways, right, for this to happen because the order between 2 and 3 doesn't matter. So that's 2 over 4 factorial. Any question about this? What about 3? Any suggestions? Um, how is it possible that player 1 will win 3 times? Well, it must be the case, right, that player 1 wins over players 2, 3, and 4, right, but lost to player 5. What's the probability that this will happen? Well, there are 5 factorial ways, right, to arrange numbers between 1 to 5. But we don't care, right, for the order between 2, 3, and 4. So that's 3 factorial over 5 factorial, right? Any question about this? Okay, so finally, right, what is probability x equals to 4? How is it possible for player 1 to win 4 times?
Is it 4 factorial over 6 factorial?
No, I don't think so. It's not over 6 factorial. Why 6 factorial?
I don't know. I need to
Okay.
think about it. Sorry.
No, nothing to be sorry about, right? It's good that you propose an answer. That's very good. Now let's take a look at this picture, right? Again, right? How would player 1 win 4 times? It must be the case that player 1 is the best, right, number among 5 numbers, right? Not 6. So it's not the pattern that we can guess, but it's the structure of the logic, right? So there's still 5 factorial ways to arrange between 5 players, because that's the max we get to now, right? 5 players. But we don't care for the order of the first 4. Oh, sorry, these 4, right? So your 4 factorial is correct, but it must be divided by 5 factorial, right? Not 6, that's all. Okay, well, very good suggestion. Okay, any question about this? Now, right, these are purely based on combinatorics argument. But what would be a good check? Let's just say, right, a safety check, right, to see at least nothing is blatantly wrong. We should always make sure that these numbers add up to 1. Okay? Because, right, in our logic, we could have slipped up something, or just the logic is wrong, right? So the fact that numbers add up to 1 doesn't guarantee that our answer is correct. But at least if our answer is wrong, it will detect it right away, right? If there's something blatantly wrong. So let's see. So we have 1/2 plus 1/6. So 2 over 4 factorial is, well, 1 over 12, right? And 3 factorial over 5 factorial is 4 5, so 1 over 20. And 4 factorial over 5 factorial actually is 1/5, right? So do these add up to 1? So it looks like a common denominator is 60, right? So we get 30 for the first one, 10 for the second, 5 for the third, 3 for the fourth, and 12 for the last, right? 40, 15, 5, so that's 20, 60, right? So that's 1. Okay. So seems okay. Again, right? Of course, this is just a safety check that you should do as an extra, right, precaution, extra caution, right? But of course, it doesn't prove definitively that the answer is correct. It's also in the logic, right? But at least we did not make any blatant mistake here. Any question? All right. So with that, let us we finish lecture 5. Let us continue on with the next lecture. Okay. So now, right after a general introduction, okay, to random variables, if you will, now we will focus on particular families of random variables. Namely, we'll focus on the discrete ones first and the continuous ones after that. So now we'll focus on discrete random variables. What do we want to know? Well, so the first thing, right, we will look at the PMF, right, the mass function of a random variable. We'll look at, right, combination of random variables via, let's say this is a mapping of a function, right? And these are mapping by arithmetic operation. Okay. The point is, basically this operation result in a new random variable. Okay. And whenever you have a new random variable, of course, the one thing you would ask is, what is it, right? What is this random variable that I just got? And so you go back to characterization again, right? Should be at least intuitive that if you combine discrete random variable, you get discrete random variables. So you would again ask, okay, what is the mass function, right, of this new random variable that I got? And this is probably, right, the reason why random variables are introduced. No, let's take it back. This is the main, right, distinction, if you will, okay, between random variables and events. Because with events, they don't take on numerical values. So you cannot take expectation variance and higher moments. You see, right? Basically, this is concepts of average. And when you want to average, you can only average numerical values. So that's sort of like the right new feature compared with, right, the probability we've been doing so far. And then, right, this is the point of the lecture that well, not the point, but when you come out of like a probability class like this, you must know, let's say, your basic random variables. Okay, these ones are the, let's say, the basic ones. What must you know? You must I guess I would put it down there, but you must memorize, literally mean memorize, the mass function, the mean, and the variance of all these random variables, with possibly the exception of something like the hypergeometric here. I think people don't really memorize its variance because it's kind of ugly. But the rest, right, people would expect you to just know off your head what are the mass functions, what are the mean, what are the variance, this random variables. And they're all discrete random variables, right? Well-known model. Okay. So I guess we start out with going right in, right, with the idea of making, right, new random variable from a known random variable. Okay. So this is, let's say, known, as in like the mass function is known. And then you go ahead and you create a new one, right, from it. Okay. Then you need to know its new PMF. All right. So for example, let's say, right, this is the random variable, right? So to make it on a table, we got -2, 0, 1, 2, right? And we got 1/5, 2/5, 1/5, 1/5, right? And so from here, we want to create a table for, let's say, x squared. Okay. So let's see, right? What values can x squared take as a random variable here from x? X squared can take value 0, 1, and 4, right? Notice the -2 and the 2 both give value 4. So, right, what effect will it have? It will have effect on the probability, right? Probably x squared equal to 0 is 2/5, 1/5. So this will be 2/5, right? How? It draws exactly from this table, right? So that's sort of like the idea, the core idea there, right? That basically the new random variables don't just come out of nowhere. It really comes from the known random variable, right? Well, you have to kind of base it on the old random variable, but you have to combine it, right? And you mix it up in different ways, right? So you trace it back. But right, how you trace it back and how you trace it back correctly is the point of this calculation. Okay, any question? So similarly, right, for example, absolute value of x will take on what kind of value? 0, 1, and 2, right? And the prop is that, right? So notice, right, that the probability are almost, right, or would say exactly the same, right, as the x squared. However, right, of course, they're not the same random variable. Why? Because, right, they don't take on the same value, right? But notice the behavior is very similar in terms of like what values it can take coming from x, because, right, basically these are both even function, so they kind of do that. Okay. And finally, right, let's say something like -3x, what effect will it have? Well, the effect it has, right, is it just turn these values around, right? For example, you have -6, -3, 0, and 6, right? With what kind of probability? 1/5, 1/5, 2/5, and 1/5. Right? Any question about this? All right. So seems easy, right? And yes, but the easiness here, right, comes from the fact that it's a discrete random variable. So you can trace value to value, point to point. The very same question will become quite icky when it comes to a continuous random variable, all right? So here we'll just try to introduce you to the way of thinking and sort of the concept, but don't take this as like easy, right? Nothing to talk about, that kind of thing. When it comes to continuous random variable, it's a completely different story. All right. So, right, Now that was right. Let's say, you know, in some way, right? You have that's like a single random variable, and you map it to another one. You can combine two, right, different random variables. Okay. Now, right, you can combine them using arithmetic argument, right? Multiply, add, subtract, divide. Those are common ways. But you can do more fancy thing, right? You can map x to a function like e to x and then add with y, right? So again, right, the point is you want to know what are its mass function, right? But notice that now, pay attention, and this idea will be right about 2 or 3 lectures later. Is not as easy as working with an individual random variable. Because not only that you need to worry about how x takes value, y takes value, but you also need to know how x and y behave together. That's why it's not an easy task. Okay. You need to know, okay, if x takes on value 3, right? Basically, you need to know the joint distribution of x and y. This is called a joint, right? So you to figure out a combination of x and y, it's not enough to know the term is the marginals, not enough to know about x and y alone, but you need to know about the interaction of x and y, namely, right, the joint. So this is like a, let's say, a more difficult, right, much more difficult operation. But, right, of course, things are simpler when they're independent. Again, right, independence does not trivialize everything, but at least, you know, it simplifies things, because basically if they're independent, then if you know their individual behaviors, you know their joint behavior by multiplying, right, the probabilities together. That is, right, if you know they're independent, then this question mark here is probably x equals to x, probably y equals to y. And so, right, that path is easy. Otherwise, right, you have to look at the joint table, right, and figure that out, okay? Which is, again, something we'll be discussing 2 lectures later. So for example, right, let's say if you have independent dice tosses, right? Yeah, let's look at x plus y. See if we are brave enough to do this. What values can x plus y take if x and y are independent dice tosses? It will be 2 to 12, right? With what kind of probability? So you see right now, again, it's not impossible, but you have to start counting, right? For example, 2 and 12 are both 2 over 36, right? 3, for example, right? Oh, sorry, it's not 2 over 36, 1 over 36, right? 3, for example, right, is 2 over 36. Same as 11, right? What are 4? That's 5, right? Sorry, rather 3, right? 10, probably 3, 2, right? Well, 5. Well, fair guess, right? Is it 4? And then 9. Right? And then what about 6? Well, again, fair guess. Right? Is that right? And then what about 6? Oh, sorry, 7, right? Like that. Right, that's done by counting. But how do we know, at least what check should we do to make sure that nothing is blatantly wrong here? We should try to add, right, to make sure that these are 1, right? So what would you have here? This is 10, right? That's 10, 20, so that's 30, 36. So at least doesn't seem like blatantly wrong, right? Any question? And so we won't do this, right? But the principle is similar. But you can see, right, hopefully that you see combining random variables is a more computationally intensive, right, procedure than, right, mapping a single random variable. And the reason is simple, right? It should take like n square operation because you have to consider how they behave jointly, even if they're independent, right? So the number of operations you have to go through is, right, I guess, order of the square, while the single one, right, is just all linear order. Okay. All right. So now let's start with that, right, concept of expectation. So expectation, right, is a universal concept, meaning that it's expectation of a random variable, period. Any random variable has an expectation, okay? But here, the reason why we break it down to discrete and later on to continuous is to give the formula. So this formula is peculiar for discrete random variable, right? And of course, where do we see that? Through this expression, right? The probability. Okay. So, but basically, right, it's a, you see, you take all the values the random variable can take and then multiply with the probability it takes on that value. So basically, right, it's a weighted average, right, of the values, right? What are the weights? The weights are simply the mass, right? The masses. All right. So what is the expectation of the roll of a fair dice? So because everything is 1/6, right? So that's, well, you know, this is 6 times 7/2, right? So that's 7/2 or 3.5, right? So notice, of course, right, that expectation doesn't have to be one of the values, right, that X can take. It can be something not that. And, right, it is referred to as a location parameter of the random variable, right? There's other that could probably qualify as location parameter, like the median maybe, right? But the average, right, or the expectation is usually the one people look at due to the law of large number association. And right, here's a reason why, right? It's location parameter and comes from the, again, right, physics. This exactly, right, if you take some sort of like, I guess, introduction to mechanics or something like that, right? you see a similar calculation where, right, basically, so here, how do you interpret the 1 and 6 and things like that? These are the location, right, of the point mass. So you have point masses hanging at these locations, right, these positions. And the mass, right, of course, are the probabilities, right? So that's it, right? Notice that I draw this, but they're not really there, right? They're just really nothing in between, right? But, or you can think of this as a thin rod connecting these masses together, right? But the rod has no mass, right? And the center of mass idea, right, is the point, right, where along this rod, where if you put a needle, right, then the set of mass will perfectly balance, right, on that needle. Okay. And of course, right, 3.5 is the location. Now it's, when you put it that way, right, for this particular example, it looks super easy because, right, I mean, symmetry, right, half here, half there. But of course, you see, even with this setup, right, it becomes, let's say, not simple or not that obvious if you just put things, right, not uniformly. Let's say at -2, you put 0.3. At 4, you put 0.05. At 6, you put 0.5, right? And let's say at -20, you put 0.15. Okay, something like that, right? So where is it, right, along this rod where you can put where you can identify a point, right, where you put a needle and it will perfectly balance, right? Again, answer, expectation, right? So it has that average value, right, taste to it, and that's exactly the location that takes on the average, right? But notice is balanced, right, in the sense of, let's say, torque, right, in physics. Notice it's not the same as the concept of the median. All right, this is a common confusion. The median is a point where 50% of the mass is to the left and 50% of the mass is to the right. For the dice example here, the expectation, the mean, is also the median because it's uniform, okay? In non-uniform example like this, the mean and the median are not the same. So the place, right, that you put along the rod that would perfectly balance torque-wise or rotation-wise, right, is not the same as 50% mass to the left, 50% mass to the right, okay? Any question about this? Right. And here, right, we mentioned another very important interpretation, which is connected to the law of large number, right? That basically is the fair price to play a game that has payoff, right, listed as the values of the random variable. And this actually, right, is the principle behind casino gambling, right? That if you go to any casino games, you can be sure that the expectation of the game, right, that you play, meaning the payout you get, is slightly negative, okay? Slightly. How much? Who knows? It changes from game to game. But the idea is, right, you would pay a small amount on average to play that game. Of course, a small amount goes to the casino's, operation and things like that. But right, no casino game will give you a zero expectation, right? Let alone a positive expectation. Because if that's the case, you can just sit there and play the game 2,000 times, and you're guaranteed that on average, right, your average winning will be positive. That should not be, right, the case with the casino. Okay, but we'll look more into this when we look at the law of large number. Okay. So the next topic, right, is, because we discuss a random variable and function, right, of a random variable, right? And we say, right, that function of a discrete random variable is a discrete random variable. So it makes sense, right, that expectation applies to it, right? So if you have a random variable, I guess I showed too much, but anyway, if you have a random variable, right, then the expectation of the function of the random variable will go like this, right? So basically you sum overall, right, the function evaluate at the values of the x, multiply with the probability x takes on those values. So again, right, this looks super intuitive. This is the weighted average, right, of the values of f of x, right? What are the weights? The weights are the probabilities, right, of x taking on those values. So what's more intuitive than that? But yet, right, this is not obvious, as in like it's a theorem, meaning that, you know, it needs to be established that is true. And right, to top it off, right, and this is not something I make up, but it's true that in some circle or in some textbook, you can definitely, or you can look it up, right? It's called a law of the unconscious statistician. Again, right, it has that sort of like teasing, making fun of, right, statisticians, but it's literally, right, somehow that name sticks. And the context is that, right, again, the statistician, I guess being very apply-minded, would take this formula as obvious, right, and need not be questioned. Okay, but in fact, again, it needs to be questioned. And why is this the case? What's not so obvious about this formula? What is the thing that is not obvious about this form? So what's not obvious, right, is that this actually does not follow the definition of the expectation of a random variable. Okay. If it follows the definition, then there's nothing to be discussed because it's obvious. It's just from definition. But if it just looks deceptively like the definition, but it's not. So the point is, this does not follow from definition. Why? Because if it's following the definition of an expectation of a random variable, then you need to multiply the values f can take with the probability it takes on those values. Okay, note. Again, this a is not meant to be connected with f of a in any specific way. It's just really all values over the support. Okay. So for example, right, to give you an idea, let's take a look at this, right? If you use the law of the unconscious statistician, which is fine, right? Not that you cannot use it. If you use it, then expectation of x squared, right, will be here from this table. Minus 2 squared times 1/5 plus 0 squared times 2/5 plus 1 squared times 1/5 plus 2 squared times 1/5. Whatever that is. Is that okay? Meaning that you take the values of x, you square, and then you multiply with the probabilities x taking on those values. Okay, that's what the law of the unconscious statistician would say. Now, if you use definition, then you would look at this table and do 0 times 2/5 plus 1 times 1/5 plus 4 times 2/5. Do we understand? So you see, potentially, right, since this reference two different tables, right? Potentially, they may lead to different calculations. But the theorem, right, exactly is that, well, the two calculations will give you the same answer. Okay. Now, while we're at this, right, let's take a look. Then you would question, then why do we even mention that law, right? Because actually, it seems like the calculation here is longer, right? It takes on 4 values for calculation, while this takes on only 3 calculations, right? So shouldn't we just stick with the definition and forget about that law? Well, the answer is no, right? This looks like the calculation by definition looks simpler, right? Deceptively simpler, because we had this table. Where does this table come from? Because we worked on it, right? We worked on it. So if you want to look at the work it takes to calculate expectation of x squared, you have to look at the work that we create this table plus that work, which now, right, would seem like more than that work. You understand? So basically, right, the law of the unconscious statistician, what it does is it allows you to reference the original table of x and then just calculate expectation of any function of x without having to figure out the new table. And that's the advantage. Right? So right here. That's what I just said. Any question about this? Okay. So let's mention this as the last slide of today's lecture. So expectation, right, has properties. And one of the coolest property expectation has is it's linear. Meaning, right, that if you take the linear combination of random variables, then the expectation would just go through. So expectation of a linear combination is a linear combination of expectations, like that, right? And the cool thing is it does this without caring about how x and y are related. X and y can be independent, can be dependent, doesn't matter. This formula is always correct. And why do you care? Because you have to compare it with variance, which we'll look at next time, where variance doesn't work like this. All right, variance is not linear. Expectation is linear. Okay. And this simplifies a lot of calculation that has to do with sum, right? Of expectation of sum. For example, right here, expectation of the sum, right, of 2 independent dice tosses will be by linearity, like that. And we have established, right, each of them is 3.5. So it's 7. Okay, that's the approach B. Notice it's so quick. What about approach A? Approach A would require you to reference this table, because that's the table of the distribution of x plus y. And this times this, plus this times this, plus this times this, blah, 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 like that. If you do all that, you will get 7. Okay. And again, right, I hope you appreciate the economy of the calculation here, right? And even cooler, like I said, right, we did not even care that X and Y are independent. It's always true, right? And we'll see that with the hat problem. We'll look at that next time. All right. Any question on this? All right, so let's continue on Friday, okay?